So we know that because spherical symmetry, we can separate out the radial part and the angular parts. But the radial part will have the angular momentum eigenvalue, right? So if I take right, yeah, in the previous, in the previous in a previous lecture, we defined, psi is going to have a part which is, say, the radial part, r of r, and an angular part, let me call it y, and it'll be theta and phi. Okay. Now, in a previous lecture, we defined a new variable, which was u of r, and u of r was related to r of r times r. So if I use u of r, then the radial differential equation that we get is something we have written out before. It looks like a one-dimensional particle, right? The equation for the one-dimensional particle. So we get this plus energy plus 2 by r minus L plus 1 divided by r squared. U of r is equals to 0. And remember that this is the centrifugal potential, or it's called the centrifugal barrier. So this barrier ensures that particles whose angular momentum is other than 0 cannot approach the origin. So all of this should be familiar from previous previous examples, right? So, I mean, just for the reference, let me write out what we defined. Like we had derived in previous class the radial equation of motion. In the full units, it was d squared u e l dr squared, and this depends on r. And then we had L plus 1 divided by 2mr squared. This is the centrifugal term. And then we had V of r, the potential, then U of EL of r, so r is not a vector, is equal to E U E L of r. Okay, so this is the special case where we are taking the unit where h is 1, m is half, e squared is 2, and v of r is minus 1 over minus 1 over r. Yeah. Okay. So now note that the potential has the form minus 2 over r, right? So, and it satisfies the conditions that as r goes to 0, r squared v of r is 0. Remember that we required this from, why did we require this? Can anyone remind me? What was the reason behind this? Okay, it seems like it's only me who is learning from this class, which is not good. So what happens if this is not true? Okay. So did we actually say anything in particular for this, or we said that this is the kind of potential that we're just going to look at by fiat?
I'm trying to remember it, but I can't. I feel like I've seen this before. But
No, I think, yeah. My what I recall is that we assumed that, and then we found two solutions to the equation. And then we rejected one of the solutions. Okay, yeah, I think a better question would be that when we do this, we get two solutions. Okay, and one solution was of the form where it was r to the power, L plus 1. Another solution was r to the power minus L. And we rejected this one, and there was a good ground for rejecting it. Do you remember that?
because it diverges.
What diverges?
As r goes to 0, the whole thing diverges to infinity.
What whole thing?
The rejected part. That's why we take b equals to 0.
The what part?
R power minus 1, minus L.
Yeah, but why is that a bad thing? Does it mean, because if I do normalization, so when I'm doing normalization, remember that we have dr times r squared times whatever function squared, right? If this comes from the three-dimensional measure, where what is the volume measure? It's in spherical polar coordinates is r squared sine theta, right? Dr d theta d phi. So if in principle this r squared can, suppose L is say 1, then the square of this is going to give me r squared. So in that case, this r squared and this r squared can cancel out, and then it will not diverge. But even then we rejected it. Why was that? Do you remember?
That I don't know.
Anyone else? But do you see why I'm saying that this is important? Because our volume measure has an r squared in it. So just because a power of r diverges doesn't mean that it's necessarily rejected, because that can be cancelled by the integral. Okay, so what we figured out was that we figured out the r component of the probability density current, and we found that as r went to 0, this contributed to infinity. So the probability current coming out of the origin was diverging. Okay. And whenever you have infinite probability, you know that something is wrong, something is unphysical. So that was the reason why we rejected, this solution, and we kept this one. Okay. All right.
Yeah, that makes sense.
Okay. And we also, and just from convergence of the wave function, we said that in the limit, when r went to say infinity, v of r should be 0, okay? Which was not the case, say, for the harmonic oscillator. But here it satisfies both of these limits. And if this were the limits, we established that the wave function had an asymptotic behavior at around r equals to 0. It looks like r L plus 1, but far away, it has e to the minus k of r, where k is square root of minus E. E, of course, is a negative quantity for bound states, and therefore K is positive. And then there was a W of R, or omega of R. And then we found a differential equation for omega of R, right? So we expect omega of R to be a completely well-behaved function, right?